Hello everyone. Today's presentation covers the composition of atoms, ions, and isotopes. I thought I would get things started with a little bit of humor here. We know that the ancient Greeks proposed that there were four elements, earth, wind, fire, and water. We can see here in the cartoon that one of these philosophers is actually starting to question that. And we know historically that there was a Greek philosopher who questioned the properties of matter. This gentleman's name was Democritus, and he actually proposed the idea that matter was made of small, tiny particles called atoms. Most of the ancient Greeks did not agree with Democritus. They believed that by accepting his ideas of matter being made of small, tiny particles, that it actually would mean that there was no such thing as free will. Now that's a very long discussion that maybe we could have at a different time. The ideas of Democritus were revived when John Dalton, an English school teacher, proposed the first scientific theory of atoms. In this, he said that atoms were the smallest particles that were going to be characteristic or representative of an element. Now, one aspect of Dalton's theory that we know now it was not correct was that he believed that atoms were indivisible, which means that they could not be broken up into smaller particles. We now know, of course, that there are smaller particles that exist: protons, neutrons, and electrons. Protons are located in the nucleus. They have a charge of +1, and their mass is approximately 1 atomic mass unit. Neutrons are also found in the nucleus. They have no charge, hence the name neutron for neutral, and their mass is also approximately 1 atomic mass unit. Electrons are located in the orbitals or the energy levels, the electron cloud. They have a charge of -1, and their mass is a lot smaller than the mass of either a proton or a neutron, being almost 2,000 times less. Please fill the information available here to your slide, which features lithium in the center. This slide is a look at the periodic table and the information that it tells us about the different elements. What we're going to find is the name of the element, lithium or sodium, the symbol of the element, which is either 1 or 2 letters, the atomic number, which tells us how many protons, the average atomic mass, which is telling us the average weight, if you will, of an atom, and this periodic table also gives us information about the electron configuration. This is not going to be included with every periodic table. Ions are charged particles which can either have a positive charge or a negative charge. Cations are particles that are going to have a positive charge. An example of this would be the sodium ion, which has a +1 charge. The lithium ion also has a +1 charge. The sodium atom would have 11 protons and 11 electrons. When that atom loses 1 electron, the number of electrons drops to 10, so I'll now have a positively charged particle. Please note the net charge for this particle would be +11 minus 10, so when I sum those, I get a result of +1. Anions are going to have negative charges. The chloride ion is an example of this. A chlorine atom would have 17 protons and 17 electrons. When that atom gains 1 additional electron, it will cause the particle to become stabilized and to also have a -1 charge. Polyatomic ions are ions built out of more than 1 atom being bonded together, and as an overall particle they have a charge. For example, the hydroxide ion is made of 1 atom of oxygen bonded to 1 atom of hydrogen. It would have a total of 10 electrons. It also has 9 protons, and it probably has 8 neutrons because the average oxygen atom has 8 neutrons. The average hydrogen atom does not have any neutrons. Isotopes. These are now different versions of the same element, and the way that they will be different is by the number of neutrons that are found in the nucleus. One example of this, we can look at 2 different isotopes of carbon, carbon-12 and carbon-14. Both will have 6 protons. If we have a nucleus which does not have 6 protons, it's not a carbon atom. What can be different is the number of neutrons. Carbon-12 will have 6 neutrons. 6 protons plus 6 neutrons gives a mass of 12, whereas the carbon-14 isotope will have again 6 protons, but now 8 neutrons to give that total mass of 14. Let's look at some additional examples of isotopes. Here we'll look at 2 different isotopes of sodium. Please note that to be sodium, they have to have 11 protons. Both will also have 11 electrons. It is possible for isotopes to become ionized, but as we consider isotopes here, we want to just assume that we're dealing with a neutral atom. Where they're going to be different is in the number of neutrons found in the nucleus of each isotope. Here we have an isotope called sodium-23. Please note again the atomic number 11 in the bottom, the mass number 23 written above. This would be an atom which is going to have 11 electrons, 11 protons, and 12 neutrons. The 11 protons and 12 neutrons give us the mass of 23. This different isotope of sodium is going to have a mass of 24. Again, 11 protons, 11 neutrons, but note the altered number of neutrons here. So 11 plus 13 gives us that mass of 14. Please note that there are other isotopes of sodium which are found in nature because in fact the average atomic mass of sodium is 22.99. So the average mass of all sodiums is actually less than the mass of either of these two isotopes, meaning that there must be isotopes which have a lower mass than 23 or 24. Here are some practice problems that students can use in order to figure out the number of protons, neutrons, and electrons in a number of different particles, including some different isotopes and some different ions. Please pause on your playback, and after you've finished, you can go ahead and check your answers. Here are the solutions to the practice problems. Please note, for the two different isotopes of bromine, their information will be the same with the exception of the altered number of neutrons giving the different mass numbers. For the selenide ion, which comes from a selenium atom, please note the addition of 2 electrons, 36 as opposed to 34, to give that charge of -2. Whereas with the aluminum ion, now we've had the loss of 3 electrons to give that +3 charge. For the sulfate ion, we would need to count up the number of protons from a sulfur and from 4 oxygens, add those all up, we get 48. We do the same thing for the number of neutrons. The number of electrons would initially equal the number of protons, but we have to add 2 additional electrons to account for the -2 charge of this particular polyatomic ion. Super collider research has revealed that there are particles even beyond protons, neutrons, and electrons. These are referred to as fundamental particles. The images here are of the CERN Super Collider in Europe. Now, for the fundamental particles, there are a lot of different examples of these, so we're limited here to showing just a few. They include quarks. Quarks are notable because they're a basic fundamental particle which makes up protons and neutrons. Protons are made of a combination of 2 up quarks and a down quark. Neutrons are made of 1 up quark and 2 down quarks. Because the different types of quarks have slightly different masses, that accounts for the slightly different mass of a proton and a neutron. An up quark also notably has a charge of +2/3, and a down quark has a charge of -1/3. Gluons are notable because they're responsible for the strong nuclear force which holds together the protons and neutrons in a nucleus. If you think about it, the protons that are all together in a nucleus should actually all push apart from each other because they're all positively charged. Photon energies and atomic spectra are important because as we consider the Bohr model of the atom, we want to understand where that model came from. So let's first talk about the particle-wave duality of light. We know that we can understand light in one of 2 ways. We can think of it as being a particle, a photon, or we can think of it as having wave properties. When we think of it as having wave properties, we can calculate wavelength and frequency as being a function of the speed of light. The equation for finding the energy of particular photons is we would use this equation here, where energy E equals hf, where f is the frequency and h is Planck's constant of 6.626 times 10 to the -34 joule seconds. Now, atomic spectra, this is something that Niels Bohr was very interested in. We know that when we add energy to atoms, they will actually glow and they'll give off only certain colors of light. These particular colors of light were given off by energized atoms of hydrogen, and this is what inspired Bohr to propose the first model, the planetary model of the atom. So in order to explain the emission spectra of hydrogen atoms, Bohr proposed this model of the atom. Now, what's notable here is the positioning of the electrons. We see that there are 2 electrons which can be held in the first energy level or the first ring. The second level can hold as many as 8 electrons. The third level can hold as many as 18 electrons. And we keep building up beyond this. So in the Bohr model of the atom, we know that electrons are particles that move around the nucleus and that they have quantized angular momentum. This means that an electron must exist in one of the energy levels. It cannot exist somewhere between those energy levels. Also notable here, we need to understand that n is the principal quantum number. This tells us the energy level which an electron is located in. The nucleus, the Z number tells us the number of protons. N tells us the number of neutrons. So the atomic mass is going to be calculated by taking Z, the number of protons, plus N, the number of neutrons. And then in quantum mechanics, we have the electron cloud model, and this is a probability model which tells us about the probable locations of electrons. One important aspect of quantum mechanics are the quantum numbers. These are numbers which describe the position of different electrons within an atom. The first quantum number is called the principal quantum number. This we give n as the symbol for that. N is going to tell us which energy level is an electron located in. Electrons can be located perhaps in level 1 or maybe in level 2, level 3, level 4. Depends on how big the atom is and how many electrons it's going to possess. Angular momentum, the symbol here is L. This is going to be calculated by n minus 1. This is giving us the subshell that an electron is located in. So if we think about this, if we have energy level 1, the angular number, the only thing that's possible is 0, which means that there's only one subshell in the first energy level, and that would be an S subshell. If we have the second energy level, now we have angular numbers going from 0 to whatever n minus 1 is. So we have 0 and 1. We could have two subshells and an S and a P. If we are looking at the third energy level, n minus 1 would be 2, so we'd have 0, 1, or 2. The third energy level has S, P, and D subshells, and this continues to expand as we move to higher energy levels. The magnetic number actually tells us which particular orbital is an electron in. This becomes really important as we consider the P, D, and F subshells. I like to think of an orbital as being like a box that can hold electrons. An S subshell has just a single box which can hold two. Let's finish the information about quantum numbers. So we were discussing the magnetic quantum number, the third quantum number. Again, this is describing the different orbitals that electrons are located in. And what we're doing here is we're finding the angular momentum value, which for an S orbital is, an S subshell would be 0. For a P subshell, it's 1. For D is 2. For F is 3. So the magnetic number is going to go from minus L through 0 to positive L. So for an S subshell, the only magnetic value that's possible is 0. This indicates that there's only one box in an S subshell which can hold 2 electrons. In a P subshell, it indicates that there's actually 3 orbitals. Minus 1, 0, and plus 1. Each of these we think of as a box which could hold a total of 2 electrons. So the P subshell can hold a total of 6 electrons. So this is why the second energy level can hold a total of 8 electrons, because in the second energy level we have an S subshell and a P subshell. So we have 2 electrons in the S orbital, and then we have 2 electrons in each of the 3 orbitals found in the P subshell. D subshell is going to have a total of 5 orbitals, 1, 2, 3, 4, 5. So this is why a D subshell can hold a total of 10 electrons, and F would go from minus 3 to minus 2, minus 1, 0, plus 1, plus 2, plus 3. So we have a total of 7 boxes or 7 orbitals, each holding 2 electrons. So an F subshell could hold a total of as many as 14 electrons. Finally, we have the fourth quantum number. The spin quantum number gives us information about the actual spin of an electron. Think of a top, either spinning clockwise or counterclockwise. Now for electrons, we refer to their spin as either being spin up with a plus 1/2 or spin down being a minus 1/2. This is indicated here with either up arrows for spin up or down arrows for spin down.